I'm going to talk about the paper I submitted, Mapping Diagrams, Function Visualization of Real and Complex Analysis and Matrix Algebra. And as a preface, I want to mention that the organizers wrote in their description of this session that the aim was to map a possible visualization research trajectory. And by visualization, they included visualization as a cognitive process, as a mathematical construct, and including new technologies, especially, or in particular, interactive dynamic software. I'm going to be talking about mapping diagrams, which are an underused visualization of functions. My paper outlines their use in the paper outlines three contexts involving what I call linear mathematics. I hope that as math educators or researchers, you will pursue the use of mapping diagrams further in your own work and investigate its effectiveness, which is the purpose of my presentation today. You can find more details in my paper and at this link. This is a GeoGebra book, so I'm going to turn now to the next page. I'm going to focus on mapping diagrams in two of the three contexts discussed in the paper. First, in beginning algebra, to visualize the algebraic steps used to solve a linear equation of the form ax plus b equals c, for example, to solve the equation 2x plus 3 equals 5, which I think you can all do. And second, in studying complex numbers, to visualize a complex linear function of the form f of x equals az plus b, where a, b, and z are all complex numbers. For example, how to visualize the function f of z is 2I times z on a unit circle. A mapping diagram in the context of real functions can be introduced to visualize a table of values. And linear functions are a key to understanding a lot of basic algebra. So here I have a table on the left and a figure on the right for the function 2x plus 3, f of x equals 2x plus 3. So in the table you see two columns. They could be done as rows, but I'm doing them as columns. And the x's, the input values go from 1 down to -3. And the related output values, the values of this function, are 5 down to -3. On the right, we have a mapping diagram which has two axes. The left axis with numbers on it, a real number line, represents the inputs, and we can see numbers 1, 0 down to -3 on this axis. And the right axis represents the second column, the target values, 3 down to -3. And we see arrows between them. For example, an arrow from -1 to 1, indicating the relationship that -1 has a value of 1 when evaluated with the function. And we see these arrows indicating some various features of the function. For example, each unit on the left gives rise to a 2-unit difference in the right. That's just an interesting thing to note in this mapping diagram, which might be thought of as a rate or a magnification factor. Now, solving equations is an important task for beginning algebra students. Unfortunately, students learn to solve equations with little visualization of the steps in the process. This may be a factor in why some students don't continue with mathematical studies beyond this beginning algebra course. Mapping diagrams can provide a visualization for success for all of the students in these courses. For example, to solve the linear equation 2x plus 3 equals 5, we use the function 2x plus 3. This is a composite of functions, actually. The function m, which is doubling x, 2x, and the function s of x, which is adding 3 to x. This is visualized below in the mapping diagram created using GeoGebra. So on the right, we have the mapping diagram first for multiplication by 2x. And then I'm going to take the results of that function and apply the mapping diagram for s, giving us the composite visualization of 2x plus 3. And here's the diagram that we had before. I can take these out for a second to show you the diagram we had before. But what I'm going to do is take out the last one because that clutters up the approach we're going to use to understanding and solving the equation. We're going to do the work on the algebra on the left-hand side of this activity. So our problem is to solve 2x plus 3 equals 5. Now the first step in algebra would be to subtract 3 from both sides. The number 5 is already showing up in our diagram in the target because that's what we're hoping to find as the result from the appropriate x being put in to give us the number 5, which we can see back here on the diagram should be over here at the number 1. But let's go through the algebra and visualize that. So the first step is to subtract 3, which I have here on the left, and that subtraction corresponds to reversing the arrow from 5. We were adding 3 to get to 5, so we subtracted. The arrow for subtraction is going in the opposite direction. It's undoing what the previous arrow did, and so that's our first step, and it takes us to the number 2, which is the result of what the first function 2x would give us. So we're looking to reverse that arrow, and that's the next step in the algebra as well, to multiply by a half, which reverses multiplication by 2, and we see the result visually on the right, giving us the number 2 with that arrow, whereas the number 1 shows up here in our algebraic step. So we have a visualization of this second step in the second arrow going to the left. Of course, there's the check, and that is to plug the number 1 into the function and see that 2 times 1 plus 3 is in fact 5, and that is seeing that arrow, the single arrow, seeing the function going back from the number 1 to the number 5. Now in GeoGebra, one of the nice features is that we can change, in this GeoGebra thing, I have made it so I can grab the point on the target and change it to 4, and you see that the corresponding algebra on the left is moving with that. So we see a dynamic way to see that the steps here are replicated for any value, 4 or 3 or 2, and the algebra steps would be the same. And the diagram is doing the same thing in its reversal of the maps. We can also, with the slider here, change the magnification factor, or the slope as some people refer to it. So let's change it to 3. And you see dynamically the 3 has changed in the function. It's also changed in the diagram. The magnification factor by 3 is now larger gaps between the inputs. And we can see also that we can change the b by, again, using the slider, we can change the b to subtracting 2. So instead of adding 1, now instead of subtracting 1, now we're adding 2 to reverse, and then dividing by 3. So this mapping diagram visualizes the algebra in these steps, and I think that's a useful connection to make for students at the beginning of their algebra, and it works further on. Looking at complex numbers, yeah, thank you. So for complex numbers, they're usually visualized early in solving a quadratic equation, and I'm going to turn to the mapping diagram for complex numbers, which uses, instead of 2 parallel axes in the real mapping diagram, 2 parallel planes in a 3-dimensional space, which I have organized here in this figure. So there's you can see the 2 planes there in this 3-dimensional GeoGebra figure. And we're going to look at the complex linear function of the form f of z equals az plus b, where a, b, and z are complex numbers, and looking at 2z, so we can see that's magnification by a factor of 2. And if you look straight down, you can see the magnification. But if you look at it this way, you can see other features of the function. And I'm going to change the 2 to a 2i. And now you can see the magnification by the factor of 2, but also the rotational factor of rotation by a 90 degrees, and providing us with this amplitude twist. The features in GeoGebra allow us to move the center of the circle and also to change the b and see the effects of that. So I hope you have seen the potential of mapping diagrams, and that researchers at this session, or who read my paper, will continue my work and just demonstrate the many benefits of mapping diagrams as visualizations. Much more work remains to be done. Thanks to the organizers for all their work in this session, and to you for attending this session. If you'd like to learn more or become involved in research related to the mapping diagrams, please contact me by email. Here's my email address, flashman@humboldt.edu, and I'll put this link up in the chat, which is to this GeoGebra book, which has many more things in it. Thanks again, and maybe we'll talk tomorrow at 3 a.m. my time.